So, let's start. So, what is also important and should be emphasized is the difference between the second and third condition. What is the difference? Here, it is a sum, as you see, like a sum, and here is the common part, right? Intersection. But the difference is that here you have a family of sets, and you sum all the family, all of these sets. So you have a sum of the whole family of sets. And here you have an intersection, a joint part of two sets only. The issue is that this family is potentially infinite. So in this definition of topology, it is important that you can sum infinite number of sets and you still are within the topology. And you can take an intersection of two sets and you're still in the topology. But if you take an intersection of infinite number of sets, like in the case of the sum, it might happen that you go outside of the topology. Okay? So that's an important difference between those two conditions. Just take it into account. Maybe it will occur important at one point. Okay. Now, also another notation is that this set X together with T, so a pair consisting of the set X and T, it's called topological space. So this is exactly topological space. And it's a formal definition. So whenever we say topological space, we mean an ordered pair of a space together with a given topology. Okay? A fixed topology. We choose one and that's it.
Is every topological space a metrical space?
No. There are topological spaces which are not metrizable. It can happen. But these are rather difficult examples.
But the inverse is true?
If a space
metrical is topological.
Yeah. If you have a metrical space and you have a space and a metric defined on the space, you are able to recover the topology from the metric, for example. Yeah? So you can have a metric-based topology, but it also means that there are other topologies on this space. Not the metric one is only one example. Okay, and one more important thing is that elements of T. So maybe I'll write it here. Every element of T is called open set. And it is also a very basic notion in topology, notion of an open set. So that's an arbitrary choice, I would say. We call those sets open. It's another word to be learned. Okay. And now I will give you the definition of continuous function, but without using any metrics. So in more general context, in this topological context. So let's say definition. Let X and Y topological spaces. When I write like that X and Y are topological spaces, I mean by that both X and Y comes with a certain topology. So I'm not writing it explicitly, but you should understand that when I'm writing that these are topological spaces, there is a given topology already chosen with X and for X and for Y. So let's imagine these are topological spaces, and then let's imagine that F acts from x to y. So this function is continuous if for every okay, so so it means that wherever I have an open set in Y, which comes from some set from X, the set from which it came is open. So to draw it in a picture, I have X, I have Y, I have a set here, which is open, and it's F of certain set, V. This is open. So it comes from V. And F is continuous if for every such V, from the fact that this is open, it is implied that this is also open.
And once again, what does it mean that it is open?
It means simply that it's an element of the topology. That's it. It's open if it's an element of the chosen topology. So for example, you can imagine that the topology chosen consists only from the empty set and the whole space, because we consider those examples, right? So that we have a question.
Because there is a problem with this definition, I think, because your function doesn't have to be a surjection, so it will not be general. Better to, because there may be open sets in Y which are not images.
No, I'm not saying that for every set in Y, but I'm saying that for every set of this type. Okay? Yeah, so that's an important remark, that it might happen that Y is much bigger, and that the image of whole X, let's say, that could be the image of whole X. And there might be some sets in Y, some subsets which are not completely not in the image. And then we just don't care, you know, because they do not apply to F. So when we are trying to speak about F and continuity of F, we consider only the images of F. The question was, before I was saying that, yeah, what is open? What is open? So it can happen that this topology, for example, here is a very simple one. So it consists only of empty set and the whole space. And then, if you look at the counter image of empty set and the whole set here, then it might be very, very simple. Anyway, we will check on some examples later. It doesn't matter. What is important is that in this definition we don't use metric at all, any distances. So we can speak about continuity of function without measuring distances. The only thing that we want to measure is that if we have if in this set we have an open set, it means that it came from an open set. So that's the only thing that we want to measure, without any distance. And we measure it by the topology, because being open means being an element of the topology. So as I said at the beginning, we use this topology as a kind of a vocabulary that enables us to speak about the reality. So we say that this function is continuous if an open set comes from an open set. And that's the only vocabulary we need. Only open sets. No distances. Only open sets. Only openness. And openness is defined by the topology, because open are those elements of those subsets which are in T, in topology, which we chose. Yeah? And as now maybe you can flash back to the moment when I was speaking about the size of the vocabulary. And you can see that if we have a very big topology, we have many open sets, then we can use many open sets to talk about objects, talk about functions, etc., etc. But then we have plenty of these open sets, and it's difficult to manage with all those open sets. So we can say a lot about the reality, but we have to deal with a large number of sets. On the other hand, we can have a very simple topology, like consisting only from out of the empty set and the whole space, like two words, empty set and the whole space. And then it's very easy to use this topology. We have a very simple language, but we cannot say much about the reality using only two words, right? Okay. Now maybe some facts about this continuity of functions. So, facts. Okay, first fact. Every constant map is continuous. Okay. Can you prove it? Do you see why it is like that? What is a constant map? Is it clear? What is a constant map?
Yeah.
Okay, a constant map is such a function that puts everything to one point. Okay? So we have like a space x, we have a space y, and the function f goes like that. That it puts everything into a single point. Every point is being assigned to this one single point in y. Let's call it y. Let's see. Okay? So it's constant because for every, if you look at it, for example, on the chart like this, you will see that it looks like that. Independently on which x we take, we always get assigned the same point on the axis of y to this x. So for example, this is a constant function. Yeah?
Are we talking about a general case or only a real number?
No, general case. That's just an illustration. Yeah? But this is a general case. So we have a function which is constant, it puts everything to one point. Why do you think it's continuous? Always, if it's constant. Okay, so let's try to follow the definition, okay? And then you will understand how it works. We want to check if f is continuous or not. So what we do, we have to look at the open sets in Y, okay? So in Y, we can have two types of sets, subsets. Subsets that contain Y, or subsets that doesn't contain Y, like this one, okay? If we have a subset that doesn't contain Y, yeah? Yeah, it's not in the definition. Now I see that the remark was important. Yeah. Okay. So let's say that.
Now you would have to know something about the
what?
Because I can't see how we could justify the continuousness of the function by means of this definition. I'm not sure if it's
the standard definition of continuity is different.
Yeah, you can define it using f2 minus 1, right?
Exactly.
Yeah,
images.
I wanted to avoid that.
Yeah, but it will be hard to justify the continuousness now because what?
Yeah, that's true. That's true.
You have no information. Okay,
Yeah, sure, you're right. So you can put it in a different way. You can put it in a different way. just to explain this situation, that if you have U, which is open in Y, then f to minus 1, so an inverse function, is open in X.
Better say pre-image, I think, because your function doesn't have to be invertible. It may be
Yeah.
function. So.
Yeah, that's true. Yeah, so maybe I'll explain that. Yeah, because we will need that. I thought we won't need that, but if we need that, then let's do it like that. If we have such situation that this is Y and this is the image of X. This is the image of X. And we have a set that in Y that partially contains elements from the image of X and partially contains elements which are not in the image of X, then we can look at this pre-image of F in the sense that we look at what from this set came from X. Is it clear or not? Yeah. So we look at only, if you look at F to minus 1 here, from this set, for those guys from here, there is no F inverse because F doesn't work here, doesn't operate here. But for those guys here, we can have elements from X that came to this point. So in this situation, when we have a set that is completely not, that doesn't have common part with the image of X, we can say that pre-image of this one is simply empty. Okay? So nothing in this set came from X. Okay? So we can say that if we call this set, for example, A, then we can say that F to minus 1 from A is simply empty. Okay? And this is in case of A that doesn't contain Y.
But is it really empty, or it's just beyond our
It's empty because
we don't know what is there, so yeah.
no, it's empty because F doesn't operate. As I said here, F is defined only for the elements of X. So if we take something that didn't come from F and we look at the pre-image of it, it is non-existent.
Non-existing as far, in the light of F from X, not in the light of at all, yes?
Yeah, it exists in Y, but it doesn't came from X.
So, yes, so it does mean that it's empty. It's empty according to this particular function, but it can be not empty. Like beyond our cognition. Yes? So
yeah, I mean these elements exist here, but if we ask from which elements they came, we say from none. There are known elements from which they came. Okay. So if we get back to this example, and if we look at from where came those elements from A, where Y doesn't belong, we say that they came from nowhere. So this set is empty. And if we look
so
at
they came from nowhere of X. Yes.
Yeah.
Okay.
And if we look at the set B that contains Y, for example, B, which contains Y, then what is the pre-image of it, of this B? So from where came Y? From where came this set? Do you see it or? Yeah, so the whole X, very well. So why is that? Because it is enough to have Y, this small y, to have the whole X in the pre-image, because Y is the image of every element from X. Okay? So if we look at any set that doesn't contain Y, then then it came from nowhere. It's empty. So, yeah. And if we look at any set that contains y, it's the whole x, right? And what we know about y, what we know about empty set and x, that they belong to every topology possible, because it follows from the definition of topology that it has to contain empty set and x. So what it means is that in case of constant map, in case of constant map, you will always get a constant map. You will always have an open set that comes from an open set, because all sets come only from empty set and x. Yeah? Is it clear or not? If something is not clear, please ask the question, because it seems to me obvious, but I don't know if it is obvious for you. Yeah. Yeah.
I do not really get the idea of constant map. Is it a function or is it a set that contains a set?
It is a function. A constant map is a function. Okay, so f is a constant map, or a function. This is synonymous. Map and function, right? Function. And it means that for every x from x, f of x is equal y. So it works like that, that for every element from here, it assigns to this element a given one particular chosen element from y. This is a constant map. And we want to check if it is continuous. To check if it is continuous, we look at from where sets in y come. If open sets come from open sets, it means it's continuous. So we check if open sets come from open sets. We look at any set we want, and it is either it contains y or not. If it doesn't contain y, it came from nowhere. If it contains y, it came from the whole space.
So maybe, I mean, maybe it's obvious, but still, this notion of emptiness, and that what is it came from nowhere,
Yeah.
I mean, it indicates some kind of non-existence. It's right, like a bit like existent beyond the very particular conditions. So I mean, this emptiness is like ambiguous here because it indicates more something that doesn't exist than something what we cannot have in grasping a cognition. I mean, isn't it like that? That this notion of emptiness like a bit changes the approach towards understanding reality at all.
Yeah, somehow, yeah, it depends on the function actually. It depends on the function, because imagine that the function f is a surjection, so it means that f, you can say it like that, but what is important from this point of view is just a simple technical question. It is not philosophical question, it's a technical question. If a given element from y is in the image of something from x, it is or not? If it's not, then it came from nowhere. Yeah, it's from empty set. You can maybe.
So
maybe you
the
can
question
write.
is like so it came from nowhere. Wouldn't be more? More strictly to say it came from somewhere else.
No, I will put it in a formal way, and maybe that will be understood then. Okay. So if I'm saying if I try to define what is f inverse of A, I'm saying that these are all the elements from x, such that f of x equals A. Not equals, but is an element of A. Okay? Right? And if it's like that, then so there are all these elements from x that f takes into the set A. So if you look at the set A and we ask what are the elements of x such that f moves those elements to A, The answer is there are no such elements. So this set is empty. Right? Yeah? Okay. So, okay, so now another example, also a very simple one. Also a very simple one. So, identity map is continuous. Okay, so what is the identity map? Identity map is the following map that for every x, maybe I write no, f from x to x, such that f from x equals x for every x is identity. Okay. And why it is always continuous? It's always continuous because if you have set here which is open, let's call it U, it's open, then where does this set come from? It comes from the set, exactly the same set U here. Why it's exactly the same set? Because all those elements are equal, because it's the way F operates. So if this one is open, then this one is open as well. Okay. Is it clear? Yeah? So, independently on what is the space where F is defined, if F is an identity map, then it is continuous. Okay, and another example. Let's say if, maybe that will be too difficult. Yeah, okay, maybe I should first say what is the composition of two maps. Okay, a composition. So, okay, let's say F and G are maps, and F operates from X to Y, and G operates from Y to Z. Okay, these are two functions. Okay, then the composition F. That's the sign. It's like a little circle. Okay, that's the sign. Little circle operates from X to Z. And how it operates? Let's say if F takes X to Y, and then let's say, okay, maybe let's write it like that. That's F composed with G works like that. It takes an element X, and then it moves it by F to an element Y, and then G moves it further to an element Z. Okay? From Z, and that's from Y, and that's from this X is from X. Okay? So F is moving elements from X to Y, so it takes X to Y, and G is moving elements from Y to Z, so G takes Y to Z. Okay? That's how it works. Okay? This is how composition works. And then the fact is that if F and G are continuous, then G composed, F composed with G is also continuous. And how we see that, maybe I'll draw it here. We have three spaces, right? X, Y, Z, and here is F, here is G. And we take an open set here, right? We take an open set here, and we try to show that this open set came from an open set here. Okay? If you want to check if F composed with G is continuous, if you want to check if this function is continuous, then you need to take any open set here and check if it came from an open set from here, right? So how we do that? We know that G is continuous because it's our assumption, right? So we look from where in Y this set comes from. And we know from the fact that G is continuous that it came from an open set here in Y. But as we also know that F is continuous, we know that this open set came from an open set in X. So from the continuity of F, we know that this set is also continuous. And in this way, we see that this guy comes from here. Okay? So we compose those two functions, which are continuous, and in this way we obtain a function which is continuous. Okay? Is it clear? Because F operates from X to Y, and G operates.
So it's not reversible, yes?
We don't care.
Because if we care, then we don't know if it really came from Y or X, and because it could be like Z came from X and then came from Y, and like we're asking what the
No, Z. We look at F or G. If we look at G, so we cannot look at Z and ask for F, because F is completely independent on Z. It doesn't operate here. F operates only here between X and Y, and G operates between Y and Z.
Okay.
So if we look at Z, we can only discuss G. Okay. And the composition of F and G operates between X and Z, and not on Y. Right? Okay, so now, having this said, we can define what is category. It's another word. So, very basic word in mathematics. Very basic word in mathematics, yeah. And we can say that a category. This is the definition of category. What is a category? Yeah? C, a category C, consists of C, which is a family of objects, then it consists of C, yeah, it's just a notation where x and y belong to the class of objects, and it says these are called morphisms. This is a class of morphisms, and composition map. Yeah. So okay, so what is the definition again? So C is a category, as we said about the topological space. We said that the topological space is a set together with topology. So now we are saying that if we want to say what is a category, we have to mention three things. First, the class of objects. Secondly, morphisms, so you can think about it as functions between the objects, and then composition of those functions. So, to draw a picture of it, you can say that you have class of objects. This is this, okay? These are objects. Then you have some functions here between those objects, between some of them. Okay? Then like morphisms. Yeah. And finally, you have something which is an operation of composing these morphisms. So if you see here a morphism from here to here and from here to here, then you can also imagine a morphism which acts like that. And this is a composition of those two morphisms. Okay? This is the composition. So it's the same like with, let's say, adding numbers. You can also think about the category in terms of algebra, and then you can have adding numbers. So for example, you can have 5 plus 6 plus 7. Yeah, and this is like a function that you have a function that brings 5 plus 6 to 11, and then another function that takes 11 plus 7 to 18. This is like one morphism and then second morphism. And you can do it at once, and you take those three elements to 18. Yeah, but we are not interested in algebra and in addition, but we are interested in topology. And this is the most general description of topological spaces, so to say, because we can say that we can speak about the category, topological category, which we yeah, we call it like top. Yeah, we can call it top. Top. It's a category. And within this top, we can distinguish some functions which are called morphisms. So that's nothing difficult in the sense that this is only vocabulary. There is no deep knowledge behind it, I would say. There is only a vocabulary, and I'm just presenting you the way in which topologicians, mathematicians talk about topology. So there is no deep thinking in it. It's just an apparatus, like a language apparatus. How we call things, and maybe it will be useful somehow. I don't know if we'll be able to reach the point today where it will be useful, but maybe it will be also useful tomorrow and the day after tomorrow, etc. Because it's very basic vocabulary at the field of topology. Yeah? So it might be useful during the next days. So once again, a category is a set together with some morphisms and composition of those morphisms. Do you have any questions here? Yep.
Maybe it's useful an intuitive description. Often one calls a category a local mathematical universe, so a sort of galaxy which is separated from other galaxies, and inside, say, the Milky Way, yeah, we are moving and constructing things, and yeah, this is formalized by a category. And mathematics, as a totality, then consists of sort of net of categories.
Yeah, that's right.
There's a topology is one category, and
yeah,
algebraic systems are it's another category.
Yeah. Yeah, exactly. So if you look at the whole mathematics as a universe, then you can restrict yourself to a certain part of it. It's a category, and you take into account only certain aspect of the objects. So in here we are saying all the time we are saying about topology. So we forget about the whole. We forget about all other structures, about algebraic structure, analytic structures, etc., etc., about metrics. We only focus on this topological aspect of the world. And in this sense, we limit ourselves to the category of topology. Yeah? And that's why it's topology. Yeah?
Can you explain again the third part, the composition?
Composition.
Yes.
So, if you see that we have objects, like for example sets, yeah? We have sets. We have morphisms between sets, yeah? With morphisms between sets. So functions, in other words, functions between sets. And as I draw it here, and you have a given set and a second set and a third set, and you have a morphism here and a morphism here. Then you can think of a morphism which is a composition of those two. So it's like not a separate being. It's like making this thing and then this thing. It's like doing it together, like adding those two operations. And that's the compositions. It is the composition of those two. So, for example, I would say. Just to give you an example, if you want to, I don't know, if you want to, I don't know, boil potatoes, for example, yeah? You can do it in 2 steps. First, you take a pot and you pour water inside, and then you take this water with potatoes and with the pot on the heating machine or something, and you boil it, right? So you can divide this process into two parts: putting water to a pot and boiling the pot with the water and potatoes. Or you can think about it as a single activity, like taking all together. So what is this point here? It enables you to compose different activities into more complex activities, let's say. So whenever you have some morphisms, so some activities in the world, you can compose them into more complex activities.
And that will still be a morphism in that kind of
Yeah. So, and this way in which you compose those morphisms tells you how this world looks like. Because you can imagine that, for example, it is a difference between pouring the water to the pot and then heating it. It's different than heating a pot and then pouring water inside. These are like two different operations. So if it is like, so the way, for example, in which you compose operations tells you how your world looks like. Yeah, and in this world of topology, your morphisms are continuous functions. So maybe I should write it explicitly. That in the world of topology, morphisms are continuous functions. In the world of kitchen, let's say, morphisms are activities in the kitchen, right? And in the world of, let's say, real numbers, you can have some functions like adding numbers. Yeah? So every world can have its own morphisms. But we are today interested in the morphisms in the world of topology, and it means that we think about continuous functions between spaces, between topological spaces. So we can compose those continuous functions. Okay, more questions?
Yeah. I'm looking for the philosophical applications of this.
Yeah.
And I just want to ask, is this concept of category, topological concept of category in any way applicable to the ontology and to this ontological concept of category? For example, can you interpret such ontological categories as substance, property, or relation in terms of this concept, topological concept of category?
I'm not an expert on this, I would say, but definitely you can try to apply that. But maybe Professor Mormann can say more about that.
The founding father of mathematical category theory was Thomas MacLean and Samuel Eilenberg, and I think they choose the word category, so to speak, to provoke philosophers as a counter concept, and maybe there is a relation between the standard philosophical categories and the mathematical ones, but it's not a direct one. It's just for, where I say, for instance, infinity belonged for a long time to philosophy, and mathematical infinity was intended to offer a precise theory of infinity, not directly related to theological concepts of infinity. So these are two parts. And I would say the best book for understanding is MacLean's Form and Function. Form and Function on the how to organize mathematics in terms of categories for elementary people who don't know much about mathematics. A bit, yes, but this would be a starting point for understanding category theoretical perspective on mathematics by one of its founders.
You know, I think that maybe we can try to look at it also from such a perspective that we can use this mathematical concept of category as a model to model philosophical concept of category. So it's like modeling the world. You can try to use, for example, Cartesian space to model reality, or you can use this category concept, formal category concept, to model certain philosophical questions and problems. Maybe also that was the intention of the founders.
Or perhaps one can model the world after the model of sets, so everything can be conceived with some effort and goodwill as a set, but this is a very poor model, and the concept of category offers a much richer model, because not only objects but also manipulation of objects is modeled in this category. So I mean, everybody knows what a set is, and then category could be considered as an enrichment of the concept of set. And then you have a natural perspective. Sets themselves are a category, another category than the category of topological spaces.
Yeah.
We can say that the modern category theory is a kind of philosophical and modern category theory also. But there is no connection, there is no direct connection, like as Professor Mormann said, between, let's say, substance and, let's say, the category of sets. But what is important, categories are not alone. Between categories are morphisms. And we can build the categories on the categories, let's say. And Sanders MacLean, he said, that was his idea, that mathematics is a kind of network of categories. And that's, from this point of view, category theory is a kind of formal ontology for mathematics, but it's a network ontology, let's say. It's not like, you know, we haven't got one category, what is the most important category. It's a kind of network ontology.
But what is important is also the fact that it is a kind of a language to speak about mathematics or philosophy or world. And the real value of it is how you use it. So it's like a language, and language as a language has a potential, but doesn't have worth in itself, I would say. So if you're skilled enough to use this language to find some interesting things or explain certain phenomena, then it starts to work. Yeah? So as I said before, what I provide here is a kind of a vocabulary, and it's your task to make a use of it, out of it. Yeah? Okay, so now there is one specific thing also. It's also a kind of notation that there are some specific morphisms that for an object, let's say X, there is a unique morphism 1x, let's say, which is identity, let's say, identity. So it's pretty trivial, yeah. So that we have a morphism that doesn't do anything. Yeah? So it takes a given set and it transforms it in a trivial way into itself. Yeah, so we have x, we act with 1x, and we get the x again. Nothing changes. Nothing changes. Yeah? So also because it's at the level of sets and at the level of elements, let's say it's also identity.
But what do you mean by unique? Unique for this object or unique identity?
Unique for this object. Yeah. But yeah, well, unique for this object, and it's also unique morphism. Yeah. So, in other words, to express it differently, whenever you have two morphisms that doesn't change anything in X, they are equal. So if you have a morphism F and morphism G, and they act on X in a way that they don't change anything, it means that they are equal. And what is important is the definition that if, let's say, F acts from X to Y, and G acts from Y to X, and if F composed with G is equal to 1, and G composed with F is equal to 1, then X and Y are isomorphic. Okay. And F and G are isomorphisms. So what it basically says is that if we have two objects, X and Y, and we have a function that F and function G, and this function, and there are those functions F and G, and they, if we compose them with each other, we obtain an operation that doesn't change anything. So if we take F and then G, it is we don't change anything. And if we go in the other side, if we take G first and then F, and it also doesn't change anything, it means that those two objects are somehow identical. Yeah? They're not completely identical, but they're isomorphic, which means they are identical with certain subtlety. So they're not completely identical, but with regard to these morphisms, they seems to be the same. They look the same.